Okay, thanks for the introduction. And today I will be speaking about joint work with my supervisors Henning, Basold, and Alfons Laarman on the optimization and synthesis of quantum circuits with global gates. So let's start with some introduction and motivation for our work. So as you might know, you cannot just compile it in a trivial manner. You need to take into account your hardware's capabilities in order to improve the performance of your algorithms or to be able to execute them in the first place. So in particular, in this talk, I'm interested in ion trap quantum computers. So one particular characteristic that these machines have is the ability to perform global entangling gates, which is a single native instruction that can entangle potentially the whole register with just one operation. So what we do in our work is we develop a compilation algorithm that converts an arbitrary quantum circuit into one that uses global entangling gates, while we try to minimize the number of these gates, because these gates are very powerful, but they are also quite expensive to execute. And with this, we are going to use the ZX calculus as a tool for this algorithm. Okay, so first of all, let's see what kind of gates do we have in this hardware. So as you might expect, we have single qubit rotations. We have the R gate and RC gate, with which we can recover the usual Pauli rotations. And more importantly, we have a 2-qubit entangling operation, which is the Mollmer-Sørensen gate, also referred to as XX gate or MS gate. With this, you can recover the more popular like C0 gates or control C gates if you add some single qubit operations around them. And more importantly for this talk is the global Mollmer-Sørensen gate, or GMS gate for short. And I don't want you to read the definition. I think just with the picture, it's quite clear what this does. So as long as in your circuit, if you have a sequence of XX gates, you can, and they are uninterrupted, you don't have any other gates in between, you can put them together and execute them all in parallel. So this instruction takes the same time to execute as just one of the individual XX rotations. So what we're going to do now is we are going to take some arbitrary quantum circuit and we're going to try to massage it in such a way that we're going to put all the entangling operations together so we can compile them with the minimal amount of GMS gates. So first of all, I'm going to quickly explain what is the ZX calculus and how one can optimize circuits with it. So we already had a talk about ZX before. So just a quick reminder, the ZX calculus is a graphical language to represent linear maps between qubits. We have a set of generators. In this talk, we are just interested in the first three. We have the Z spider, the X spider, and the Hadamard gate, which is a dashed blue line. Now, what is most interesting about this language is we have a set of rewrite rules that is complete for the language, which means that if we have two ZX diagrams that represent the same linear map, we can always go from one to the other by just applying this set of rules. And now ZX calculus has been used for a lot of applications. In our case, we're interested in circuit compilation and optimization. So let's quickly see how one would do this in the general setting. So you can present a quantum circuit very easily as a ZX diagram. So this is how a 4-qubit quantum circuit would look like with using just ZX diagrams. So you clearly have the single qubit gates are just these spiders with one input and one output. And then we have the entangling gates are the ones that can connect the wires together. Now, if we take this representation of a quantum circuit and we apply a set of rewrite rules to them, for the people familiar with this, I'm talking about local complementation, pivoting, and so on. You can simplify the diagram in some way. In this case, we reduce the number of vertices in the diagram, but we are still representing the same linear map. Now we have a diagram that represents the same unitary, but that does not look like a circuit anymore. So if we want to recover a quantum circuit from this, we need to do a process that is called circuit extraction. So really quickly, circuit extraction works as follows. So we start from the right of the diagram, from the outputs. we label all the output vertices as the frontier vertices, and then we're going to do operations on this frontier in such a way that each operation extracts a quantum circuit, a quantum gate, until we have moved the frontier all the way from the input, all the way until the inputs in. So we consume the whole diagram, and by doing this consumption of vertices and so on, we generate gates in our circuit. So for example, CNOT gates, what they do is simplify the connectivity of the frontier vertices with its neighbors. So you can see we applied two CNOT gates here, and we managed to make vertex B have only one neighbor. This allows us then to remove vertex B by creating a Hadamard gate. Then we can remove the phase on vertex W by extracting a C rotation. And then if we have connections between frontier vertices, we can remove them with control C gates. Now what we're going to do is modify the circuit extraction algorithm, so this is known from the literature, in such a way that the circuit that we extract is going to be more amenable to fit GMS gates. So we're going to take the entangling operations and we're going to extract them in such a way and move other gates around in order to compile the circuit with the least amount of GMS gates. So let's see in more detail how we do this. First of all, we show that if we have a CNOT circuit that has commuting CNOT gates, so all the CNOT gates in the circuit commute, we can always compile this with only one GMS gate. And what we're going to do is we're going to create layers of commuting CNOT gates in our circuit in order to just compile only one layer with one GMS gate. So in particular, during circuit extraction, when you're extracting CNOT gates, you always require only one GMS gate in order to advance the frontier. So in particular, you need what is called a FANOT gate, which is a CNOT circuit that has only CNOT gates with a shared control qubit. So these CNOTs also always commute, and we are able to compile with only one GMS. So what we do for this part of extracting CNOT gates is that we encode the problem of simplifying the frontier with commuting CNOTs as a linear program, and we throw it to a solver and get the results. So we're not going to go through the linear program, but the idea is that we're going to extract as many vertices as possible with the least amount of CNOTs, with the condition that all the CNOTs must commute always. In this case, we are always advancing the frontier with one global gate. Apart from this, we also do peephole optimization during the extraction. So I'm going to explain some of the things that we do, for example. So when we have single qubit gates, when they do not collide with one GMS, what we do is we move it outside, so we can free up the qubit on the bottom, for example, here, in order to fit more entangling gates in the future. But when, in the case of the Hadamard on the top, for example, we would not be able to commute it past the GMS, so in this case we block this qubit for the future, and we're not able to join more entangling operations into this global gate. So control C layers that we extract, we divide them into two sets. So always a control C layer can be compiled with one GMS, but we found that it's better to actually divide it into two parts. We send the part that commutes with a GMS away, and then we compile the rest with one GMS. So in this case, we have here a set of qubits that are able to later join the GMS, which is better to join CNOTs together than, for example, compiling this control C layer and this GMS together with one GMS. This is because when you compile a control C layer using GMS gates, you need to surround it by Hadamard gates, and this later get in the way if you want to make a more dense global gate. And lastly, CNOT layers. What we do is first of all, we do not assume that they are commuting. So in the case that you prefer to use a different algorithm to simplify the frontier, this still works, this too. And what we do is try to push as many CNOTs into global gates that we have created before in order to arrive to the least amount of gates. So for example, here we have 5 CNOTs that they all commute except for the first one that does not commute with these 2. So we would need 2 GMS gates to compile this circuit. But instead, if we push these 2 CNOTs to this gate, and then we compile this other 3 with 1 GMS, then here we save one global gate in the end. So we implement and integrate this algorithm in P6, which is the Python library for Serex calculus. And we compare it with a naive algorithm and with Qiskit. So in here I'm showing some results. We check the final number of single qubit gates with the final number of GMS gates and the total time in milliseconds that it would take to execute the quantum circuit. And in general, we see that the linear program algorithm works better in most of the cases than the rest, followed by the peephole and then Qiskit. So I run this in 3 benchmarks. It's MQT, quantum chemistry, and Quasam bench. And in most of the time, this is what we see, the linear program works much better, but there are some cases in which Qiskit works better. So when I was looking at this manually, I saw that this is in case when circuits are really constructed in such a way that the entangling gates can never be compiled with one global gate, then Qiskit, which has a better single qubit gate optimizer in the end, performs better. Because what you do is then you are not able to simplify the circuit or use these global gates to put CNOTs together, for example. But this is, from what I have seen, is quite rare. In general, our tool works much better. Okay, so I'm going to jump now to conclusions. So we have presented a quantum synthesis and optimization algorithm that uses ion trap quantum devices, in particular the global gates. For this, we use the Serex calculus, in which we take the circuit extraction algorithm and we change it in such a way that we reframe it as a synthesis algorithm. And we demonstrate improved performance compared with other methods. And I think as future work, I think it's quite interesting to look at a generalization of these global gates, which allows different interaction strengths between qubits. So in this case, for example, if you were working with phase gadgets, you can, if you manage to put them together, then this could also be compiled with global gates. But also in general, changes in the secret extraction algorithm for Serex calculus, I think this can be explored further to treat this as a synthesis algorithm, because you have a less restrictive way of representing a quantum circuit, which is a simplified Serex diagram. So you would be able to perform better instead of just working with peephole rewrites when doing synthesis. And here I have some references on if you want to know more about global gates or about secret extraction with Serex diagrams. And thank you for listening.
Thank you, Alejandro, very much for the talk. Questions, please. Oh yeah, over there.
Yes, thanks for the talk. You might not realize this, but your work is actually more general than just GMS gates, because you can, in the surface code, also execute these CNOT fan out and fan in gates with Deth1. So basically, all of your things that you do immediately also translate to surface code compilations. And yeah, I also did a similar work with a colleague of mine, where we also used ZX calculus for something similar. And so yeah, what we did is we didn't use this extraction algorithm, but we focused basically on Clifford subcircuits. And within the ZX calculus, there's this normal form or something. I'm not sure. ZX experts will probably punch me now, but there's this normal form which basically brings the circuit into a form where there is a lot of C-nots in the middle and some other stuff around. And this can be used to also apply these techniques. So yeah, thank you.
Yeah, I think that actually this was a work by Sebastian, I don't remember his last name. Yeah, I met him last year and we actually discussed this. Yeah. Yeah. Thanks.
So was the circuit extraction approach new to this work, or is it the same thing that physics is doing when it extracts the circuit from?
So the difference that we do is in the part of extracting the CNOT gates, and then the peephole rewrites that we do during the extraction. But the whole process of then after simplifying the frontier, see which vertices you can move, and then pushing the Hadamard gates and the RC gates that we have seen in the beginning of the talk, this is the same.
So presumably this wouldn't work on if like an arbitrary ZX diagram, because some ZX diagrams can't be transformed into circuits. So it's because you're just maintaining the circuit structure whenever you do the optimizations?
Yeah, exactly. So this all, if you're familiar, this all preserves the flow of the diagram. So we assume that we have a circuit as an input that we want to compile for this certain hardware. So for this, yeah, we try to keep the flow of the diagram. So if you have seen, actually the gates that we extract are the same that are extracted in this paper over here, because in this we already guarantee that flow is preserved, so we don't extract directly, for example, these phase gadgets.
Okay, so that makes things easier.
Yes.
Okay, thank you. One more time.